Okay, so today we're entering a new chapter. The topic of this chapter are these things called linear transformations. Okay, and at the beginning of the course I said that linear algebra is not about matrices. Right? It's not the study of matrices, it's actually the study of linear transformations. So in some sense we're only now getting into the actual topic. Right? And everything that happened before was basically preparing us to understand, to talk about this topic. Okay. So just like how we said that vector spaces are an idea that is very fluid and sort of shows up. It's not just Euclidean spaces, but vector spaces can show up. Can be used in multiple settings. The idea of a linear transformation is also a very general and useful idea. Okay, so I'm going to start out with the abstract definition, which will seem a little strange, but then I'll show you that we're actually pretty familiar with linear transformations already. Okay. So you start off with vector spaces. Okay, so V and W are vector spaces. Okay, and you have some map T going from V to W. So a map from V to W. Okay, so in other words, it's a function basically that takes in something in V and then gives you back something in W. Okay, so it takes in something in V, gives you back something in W. Okay, if T of V1 plus V2 always equals T of V1 plus T of V2, and T of alpha V1 always equals alpha of TV1. So this is for any V1 and V2 in your vector space and any alpha in the real numbers. Okay. If T has these two properties, then we say T is a linear transformation. From V to W. Linear transformation. And for some reason, all the teachers when I was an undergraduate abbreviated this as X form. So the X was, for some reason meant trans. So this is the abbreviation that I always use, transformation. Okay. So then we say T is a linear transformation from V to W. So just thinking about this, this definition, you see that what it's saying, what it's dealing with, are the basic operations of the vector space, right? What are the basic things you can do in a vector space? Well, you can multiply by a number, right? You can scale your vector and you can add vectors together, right? You've got vector addition and you've got scalar multiplication, right? And so linear transformation has to do with those two operations, right? That the transformation of a sum is the sum of the transformations. Okay. The transformation of a scaling is the scaling of the transformation. Okay, right? In other words, you can either add in V first and then transform over, or you can transform these guys over and then add in W. Right? You can use the addition from V first and then transform over, or you send them over and then use the addition in W and you're going to get the same thing. Okay, so notice that these two pluses are actually different pluses, right? This is plus in V, this is the plus from W. Okay. Similarly here, you either scale the guy in V and move it over, or you move it over and then you scale it in W. And either way is fine, right? So one way of saying this is that the linear transformation preserves the vector space structure. Okay, preserves, like to some degree, preserves the structure of the vector of V. Okay. Okay. So let's give some examples. Here's the simplest one. Take any matrix in Rn, or I'm sorry, Rm plus n. Okay, take any matrix, right, and define T sub A as a map from Rn to Rm define it by saying Ta of V is just AB. Okay, so just left multiply by V, by A, right? So Ta is the linear transformation that just says left multiply by A. Right? You know that if you have something in Rn and you hit it with the m by n matrix, you're going to get something in Rm. Right? Something in, right? If this guy is in Rn, it's an n by 1 matrix. A, right? A is n by n, and so AV is going to be an m by 1. Right? So you can think, right? This. Right. Left multiplication by A is a map from Rn to Rm. Right? Is that clear? Everybody okay? Right? Okay. And you notice that, observe that if I take Ta times the sum, let's say U plus B, well, that's A times U plus B. Right? That's A times U plus V, right? But that's the same thing as A times, that's the same thing as AU plus AB. That's TA of U plus TA of V. Right? So you see that we satisfy the first property, right? That if you take the transformation of a sum, you get the sum of the transformed guys. Okay? Take 10 seconds and write down why property 2 also holds for practice. Okay, so we want to look at TA of alpha V, right? Well, TA of alpha V is just alpha, I'm sorry, A times alpha V, right? Which is what? Alpha times AV, but that's alpha times T sub AV. Okay, so yeah, so the second property also holds. Okay, so left multiplication by some matrix is a linear transformation. Left multiplication by some matrix is a linear transformation. Okay. Okay. Let's do another example. Let's define a map from R2 to R2. And what this map is going to do is going to take some xy and it'll give you back x comma 0. Okay. So it starts off with xy and it gives you back x comma 0. Okay, I think I haven't introduced this notation before, this is mapped to this. Okay. So in other words, L of xy equals x comma 0. Okay. That's a more familiar notation. Yeah, right.
Are these like different from functions?
No,
Okay.
right? They're just, you can think of it as a function from here to here,
Okay.
right? Yeah. Yeah. But it's a special kind of function that satisfies these properties.
Okay. So not all functions satisfy this property?
No, no.
Oh, yeah.
Yeah. Like for example, here's, if I have f of x equals x squared, right? Is that a linear transformation?
No.
No, right? Because that would, if it were a linear transformation, that would mean that this equals this. In other words, x plus y quantity squared equals x squared plus y squared, right? Which is something I often see people, like students seem to hope for this in calculus class, but it's not true. Yeah, there's some sort of like people would like this to be true, but it's not true, right? Right. Yeah, sort of as a digression, is f of x equals x plus 1 linear? No. Why not? If I take f of x plus y, do I get f of x plus f of y? No. Right? No. Okay. This is, so you might be fooled because you think, well, the graph is a line, right? So it's got to be linear, right? But in fact, we call this thing an affine map, not a linear map. One of your homework problems will be to show that if it's a map from R to R and it's linear, then it has to be a line through the origin.
And for other ones like f of x equals x squared, is that considered a nonlinear transformation?
We don't really call it a transformation.
Okay.
It's a nonlinear function. Yeah. Okay. Okay. So let's come back here. This is our second example, right? So let's think about it. So pictorially, I have good markers today. Pictorially, what does this guy do? What does L do? Well, can anybody see what it does sort of geometrically? Abel?
Doesn't it just like get rid of the y and
Make it a what?
vertical?
Make it a vertical line? Well, you mean a horizontal line?
Oh,
Yeah.
Sorry.
Yeah.
X.
Yeah, basically, right? So you have you have some guy a comma b, and what does it do? It gives you a comma 0, right? A comma 0 gives you the vector a comma 0, right? So it takes your vector and says it projects. It's what's called a projection. So it projects the vector down onto the subspace, the x-axis. What's wrong?
But like, aren't projections supposed to be like components of that across like the two axes?
This is not the same word. Not the same word. Yeah. This is what's called an orthogonal projection. Okay. Okay. So you take your vector and then you take a shadow of it down onto the x-axis, and that's your output. Okay. Okay. So let's think. Right. Does L of one vector plus another vector equal L of the first guy plus L of the second guy? Right? if I have two vectors and I add them together and then project down, do I get the same thing as if I projected down and then add them together? You guys are more hesitant now. I don't. What?
Can you repeat what you just said?
If I have two vectors, and I add them together and take their projection, do I get the same thing as if I took their projection and then added them together? Yeah, sure. So like geometrically at least it seems to make sense, right? Right. Algebraically you would say, well, if I've got x1, y1 plus x2, y2, is that the same thing as L of x1, y1 plus L of x2, y2? Right? The answer is sure, right? Because here you're going to get L of x1 plus x2, y1 plus y2, right? Which is just x1 plus x2 comma 0, right? And over here you're going to get, this is going to be x1 comma 0 plus x2 comma 0. And so you get x1 plus x2 comma 0. Right? And those two are the same thing. Right? Okay, and, right, so this is property 1, property 2, similar, right? If I take L of alpha times x1, alpha times xy, is that the same thing as alpha times L of xy? And the answer is yeah, same sort of reasoning, right? Okay, so this is also a linear transformation. Okay. Yeah.
So linear transformation can only go from B to W. It doesn't have to be the same. It doesn't have to hold the same properties from W to B.
No, it's just a one-way. It's just a one-way thing. Yeah. Yeah, you don't. I mean, it's not even clear that you can come backwards, right? Right. So I think what you're asking is, does it have to be that the inverse map is also a linear transformation? But it's not even clear that there is an inverse map. In fact, this one doesn't have an inverse map, right? Because if I've got multiple things that get mapped to the same vector, and I can't go back from here to here, right? I have no idea. If I say, what did I start off with? The output was a comma 0. What did I start off with? I'll give you $1 billion, right? If you guess what I'm thinking of. Right? You're wrong. Right? Right? You can't go back. Right? There's no inverse map for this guy. Okay. It is true. What is true, and this is something that we're going to see. We'll need later, is that if there is an inverse map, it also turns out to be a linear transformation. It's forced to be a linear transformation. Okay, so that's sort of interesting. So if there is an inverse map, you're sort of guaranteed, you can see that it has to be a linear transformation. Okay, number 3. So again, let's define a map from R2 to R2. This map will be is the counterclockwise rotation of V through theta degrees, theta radians, sorry. Okay, so if I say like theta is pi over 2, then my map is going to rotate everything by pi over 2. Right? If this is my V, then this would be T pi over 2. Right? Just takes your guy and then rotates it by pi over 2. Okay. So, wait, I forgot to say something. Notice, the map, if I let A be 1, 0, 0, 0, so let A be 1, 0, 0, 0. Okay. Then A of xy is x comma 0. Right? 1, 0, 0, 0 times xy is going to give me x0. Right? And so this L is actually T sub 1, 0, 0, 0. Right? Using the notation from the first one. This L actually can be obtained as left multiplication by a matrix. Okay, so this L comes from some matrix. Is that all right?
Sorry, can you go over that again?
Yes. Okay, so remember in the first part here, we defined this T sub A. T sub A means left multiplied by the A matrix. Okay? If my matrix is 1, 0, 0, 0, I get L. I get L. So L is,
Okay.
L corresponds to left multiplication by the 1, 0, 0, 0 matrix. Okay. This matrix arises from, I'm sorry, this linear transformation arises from a matrix. Okay. Okay. Let's think about this. Is this thing a linear transformation? Is rotation by an axis, rotation by some angle, a linear transformation? Okay. If I take a vector and I scale it and then I rotate it, do I get the same thing as if I rotate it and then scale it? Sure. Right? If I have two vectors and I add them together and then rotate them, do I get the same thing as if I rotate them and then add them? Yeah, the same thing. Okay, so at least geometrically, you believe that that this is a linear transformation. It is a linear transformation. So this actually is a linear transformation. And what happens is that it actually corresponds to the matrix cosine theta, negative sine theta, cosine theta.
It's cosine and negative sine, not cosine minus.
No, right, this is negative sine. Cosine theta, negative sine theta, cosine theta. Okay. So it actually turns out that this t sub theta is t sub A, corresponds to left multiplication by a matrix also. Okay. So yeah,
Is it possible to say that any linear transformation can be represented as left multiplication?
so yeah, that's what you should be thinking, right? That's your suspicion at this point. Like, every linear transformation is just some matrix, right? It's just left multiplication by some matrix. Okay, so here's example number 4. Let your vector space be P sub n, polynomials of degree less than n, and then let your linear let your map be D. Okay, D, which is let D be differentiation. Okay, so you take your polynomial and you hit it with D. Right? You differentiate it. You get another polynomial. That polynomial is still in your space, right? Because it just decreases the degree. Okay. Is this a linear transformation? Is this a linear transformation? Talk to somebody nearby. Say yes or no.
That's just the map that you're using. That's just where you're
Okay, so is it a linear transformation?
It is. Yes.
Yes, yes it is. Right? Because in order to check it, right, your question is, if I have two polynomials, p and q, and I add them together and I differentiate them, do I get the same thing as if I differentiate each one and then add it together?
Yeah.
Sure, right? You know that, right? The derivative of a sum is the sum of the derivatives. Right? That's something that you saw in calculus. Right? Is it true that the derivative of a scalar multiple is the scalar multiple of the derivative? Also true. Yes, right? The derivative of something like that is going to be the multiple of the derivative. Right? So D is a linear transformation. Now, does it correspond to a matrix? To left multiplication by a matrix? In other words, is there some matrix that you can multiply your polynomial by and get the derivative?
Yeah.
So you have your polynomial here. I've got my polynomial 1 plus x squared, and you're going to tell me that I can multiply this by some matrix and get 1 plus 2x.
DDS.
So you put a d in here?
D over dx. Yeah, like differential.
Okay, so the answer is no. The answer is no, but yes. No, but actually yes. So what we'll see later is that that the thing to do is to take a basis and then get the coordinate vector for this guy. Then there'll be a matrix that transforms the coordinate vector of this into the coordinate vector of the derivative. Okay, so no, but yes. So it's not directly represented by a matrix, but its behavior can be captured by a matrix. Okay, it can be represented by a matrix. Okay. But we're gonna, if that's opaque to you now, that's as it should be. Okay. 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 Now we're going to do something that's very, very uninteresting, but we're going to do it anyway. Okay. So basic properties of linear transformations. Okay, so this is sort of along the same lines as, do you remember when we first introduced vector spaces, then we proved a bunch of not interesting properties, okay, right, using the definition of the vector space, right? That's basically what we're going to do here, okay? So, game is this. Suppose that let L from B to W be a linear transformation. You may see sometimes this notation, LDW. This means the set of linear transformations from V to W. I don't use this notation often, but it's a common notation. Linear transformations from V to W. Anyway, let L be a linear transformation from V to W. Then when L will take the zero vector in V and turn it into the zero vector in W. So L preserves the zero vector. Okay. 2, L of the additive inverse of a vector is the additive inverse of L of the vector. So L preserves additive inverses. The additive inverse of V gets sent to the additive inverse of L of V. not the most exciting thing. So let's prove them quickly and get out. So the first one, right, since L is linear, L is, a linear transformation, we know that L of alpha v equals alpha of L of v for any alpha and any v. Right? Well, just let alpha be 0. Let alpha be 0, and we get that L of 0 times v equals 0 times L of v. Okay, but when we proved the boring stuff earlier, we noted that 0 times anything is going to be the 0 vector, right? That 0 times v is the 0 vector, right? And 0 times the sky w is going to be the 0 vector of w, right? So you get L of the 0 vector in v is the 0 vector in w. Okay. Equally uninteresting is the proof of the second part. I don't remember if we did this or not. So one of the students in the first class who was awake said, didn't we prove that -1 times a vector is the additive inverse of that vector? Did we prove that when we introduced vector spaces? Actually, I have my notes here so I can check. Yes, we did. Yeah, it was the third of the boring properties of vector spaces. Okay. Okay, so we just use that. Use this fact. We say, well, look, again, L of alpha v equals alpha LV, right? So let alpha be -1. We get L of -1 times v equals -1 times L of v. So that tells you that L of the additive inverse is the additive inverse of L. Okay. So yeah, I gave a even more boring proof in the first class. Okay. Anyway, so some properties. In some sense, this is just practice for you, like. How do you use the basic properties of linear transformations to prove things? We're going to do more complicated stuff than this. Okay, we're going to do more complicated stuff than this, but you see that that this property gives you these other. You use this property to get these other properties. Any questions? Any questions? Okay. Okay. Let's go on to some other important ideas. So, a couple of other ideas. One is called the kernel, and the other is called the image. So here's the definition. So again, you have T going from V to W, a linear transformation. Right. You can see why people use the other notation. Right? I can just write this, right? T is a linear transformation from V to W. Right? This is more precise. Okay. The kernel of T is defined as everything in the domain that T sends to the zero vector. Okay. Everything in the domain that T sends to the zero vector. Okay. This is something it's pretty close to another notion that you've seen before, right? The null space, right? The null space of a matrix is everything that the matrix sends to zero when you left multiply by the matrix, right? So if I have some matrix, then the kernel of T sub A is the same thing as the null space of A. Right? The kernel of T sub A is everything in Rn that gets mapped to zero when you left multiply by A. That's the same thing as the null space of A. The kernel of T sub A is the same thing as the null space of A. It's just that null space is a term that we use for matrices, and kernel is a term we use for linear transformations.
Why is it the kernel?
I have no idea. I have no idea. Why the kernel? Yeah. I don't know. What does this have to do with? I don't know. Yeah. Okay, so that's one thing. Mark, kernel of T is a subspace. And just like the null space is a subspace, the kernel of T is also going to be a subspace. Right? Because if you have two vectors in the kernel, then remember what we need to do to show something is a subspace. You have to show it's closed under addition and closed under scalar multiplication, right? So if you have two guys who get sent to zero, is their sum also sent to zero? Is their sum also set to zero? Right? Sure, right? Because T of V plus W would be T of V plus T of W by linearity, but that's zero. Right? That's going to be 0 plus 0, which is 0. Right? Another important property. Okay. Is alpha V in the kernel? Right? If V is in the kernel, is alpha V in the kernel? Sure, right? Because T of alpha V would be alpha of T of V. So that's alpha times the zero vector, so that's just the zero vector. So the kernel of T is a subspace of V. Okay. Second notion is the idea of something, the image. So again, you have a linear transformation. The image of T in T is defined as everything that comes out of T, right? All the outputs. Right? It's a collection of all outputs of your linear transformation. I should say the book's definition of the image is a little different. So the book calls this the range of T. The book calls this the range of T. It's more usually called the image. the book has a different definition of image. We're not going to really use it. If you want to read it, you read it. I don't think we need it, actually. Anyway, let me give some examples of kernel and image. Let's go back to example 2. When we were talking about linear transformations, right? We have this guy which was L of AB is A comma 0. Right? A comma 0. What's the kernel? Who gets sent to 0, 0? What vectors get sent to 0, 0? 0b, right? Any vector 0b is in the kernel of L. Right? In other words, the whole y-axis, the y-axis is the kernel of L. Right? The y-axis is the kernel of L. What's the image of L? Well, it's all outputs, right? It's going to be the x-axis, right? The x-axis is the image of L. Okay. Second example. T theta, rotation by theta. What's the kernel of T theta? Who gets sent to the 0 vector? Who gets rotated to the 0 vector? The 0 vector. That's it, right? Only the 0 vector, when you rotate it, ends up at the 0 vector. Right? So the kernel T theta is just the 0 vector. What about the image of T theta? What kind of things can you get out as an output? Anybody want to say? What can you get out from, what can you get as an output of the rotation guy? I can get, for example, can I get this vector as an output? Sure, right? Because if I rotate this guy theta degrees this way, then T theta of that will be this thing. Right? So I can get anything I feel like, right? I can get any vector in R2. Right, as an output, right? Just if I want this guy as an output, I just rotate it this way, and then T theta will rotate it back, right? And that'll give me back what I got when I started. Okay. Okay. Last example. Differentiation. What's the kernel? What gets set to 0 by the differentiation operator? Constants, right? So constant functions. Constant functions, right? Anything with a polynomial is just constant. Okay. What's the image? What's the image? Remember, space was Pn. What's the image?
Pn minus 1.
Pn minus 1. Because you're going to lose a degree when you differentiate. Okay. Okay, so maybe this gives you some sense of things. It should also sort of make you a little bit curious, because the kernel here is one-dimensional. The image here is n minus 1 dimensional, right? You've got 1 and n minus 1. Here you've got 0 dimension and 2 dimensional. Here you've got 1 dimensional and 1 dimensional, right? Right? There's some relation between, right, the dimensions of these spaces and the dimension of the domain. Right? They add up to the dimension of the domain. Okay, that's it. That's it for today. We'll do more complicated stuff later.